Chapter 10, Part 3, Evaluating Cost Drivers and Nonlinear Models. Okay, to make a good decision about the best cost driver, an understanding of both operations and cost accounting is helpful. And that's what's fun about a cost accounting job, because you're really on the floor a lot and you meet a lot of different people. Whoops. The three criteria commonly used are economic plausibility. When presented with two or more possible cost drivers, each must be economically plausible to be considered. And goodness of fit. Check the residual term. Generally, shorter is better and will result in a more accurate estimate. And the significance of the independent variable. A flat or slightly sloped regression line indicates a weak relationship between the cost driver and costs. Now, the significance of choosing the best cost driver to estimate costs is the decisions that follow. Using the wrong driver or having misestimated costs can lead to incorrect and costly decisions. And it's really the opportunity costs that we don't capture, too, that could be worse, because you might make a decision to go along with one product when another one that you didn't do perhaps would have done a lot better. Now, estimating cost drivers in an activity-based system doesn't differ in general from what's been discussed. Since ABC systems have a great number and variety of cost drivers and cost pools, managers end up estimating many cost relationships, and they will do so using the same methods, taking special care with the cost hierarchy. If a cost is batch level, for example, only batch level cost drivers can be used. So when choosing among alternative methods, managers trade off level of detail, accuracy, feasibility, and costs of estimated cost functions. And increasingly, managers are using quantitative analysis to determine the cost drivers of activities. Now, cost functions are not always linear. We wish they were, but they are not. A nonlinear cost function is a cost function for which the graph of total cost is not a straight line within the relevant range. And we've got some examples on the next slide. Okay, some examples of nonlinear cost functions include economies of scale, where you produce double the number of advertisements for less than double the cost. Okay? Or quantity discounts. So direct material costs rise, but not in direct proportion to increases in quantity due to the nonlinear relationship caused by the quantity discounts. All right. And then finally, step cost functions. Resources increase in lot sizes, not individual units. So, all of these things could be operating when you're trying to do an estimate. Another example of nonlinear cost functions include a learning curve. That's a function that measures how labor hours per unit decline as units of production increase because workers are learning and becoming better at their jobs. And then an experience curve. This curve measures the decline in the cost per unit of various business functions as the amount of these functions increases. It's a broader application of the learning curve that extends to other business functions in the value chain, such as marketing, distribution, and customer service. Okay. Now, I like this slide. It might be easier to see in your book, though. This is kind of small. So we've got three panels. Panel A shows how the cost of direct material rises more slowly as a result of quantity discounts. Okay, so here your slope coefficient is $25 per unit. Here it's 15, and up there it's 10. Okay, so that's a big difference. Panel B shows how costs remain the same over narrow ranges of level activity at each relevant range. Here we have units of production and setup costs. Okay, so that's what would cause like that step. And panel C shows a step fixed cost. So these are big, big giant steps like this. The biggest difference between panel B, step variable cost, and panel C, step fixed, is the range. Panel C shows how costs that remain the same over a much wider range due, of course, to the nature of fixed costs. Okay? So these are nice graphs, though. They really give you an idea about how a nonlinear function can look. And for many companies, learning curves and experience curves are key elements of their profit maximization strategies. They're used to reduce cost and increase customer satisfaction, market share, and profitability. And here we see two learning curve models. Cumulative average time learning model. Um, Cumulative average time per unit declines by a constant percentage each time the cumulative quantity of units produced doubles. Okay, so cumulative average time learning model. So every time the cumulative quantity doubles, the average time per unit declines by like a constant percentage. And the next one is an incremental unit time learning model. The cumulative average time per unit declines by a constant percentage each time the cumulative quantity of units produced doubles. Okay? The incremental, I can't even say these, incremental unit time learning model, incremental time is incremental time needed to produce the last unit declines by a constant percentage each time the cumulative quantity of units produced doubles. In other words, the more you do something, the more the cost is going to go down. All right, and these are actually estimated with pretty wild graphs. And I'm sure you can see all the detail here. This is in your textbook, though. This is Exhibit 10, and this is an example of a cumulative average time learning model, where the cumulative average time per unit declines by a constant percentage each time the cumulative quantity of units doubles. As the number of units produced doubles from one to two, no, 2 to 4, sorry. 2 to 4, 1 to 2, the cumulative average time declines from 100 hours to 80% of 100 hours. And as the number of units goes from 2 to 4, the cumulative average time per unit declines to 80% of 80 hours, or 64 hours. Okay, so it actually works. And in this example, a unit time learning model, the incremental time needed to produce the last unit declines by a constant percentage each time the cumulative quantity of units produces doubles. So with this model, the 80% means that when the quantity of units produced is doubled from X to 2X, okay, the time needed to produce the corresponding unit is 80% of the time to produce the first unit. So let's see an example of that. This is awfully hard to read. These are our 40.96. Yeah, it's the same chart. 60. Here's their example here, though. So D14, 250.21 equals D13, 180, plus B14, 180 plus divided by 70.21. Oh, well, take a look at the detail on this in the book. You'll not have to calculate these things or produce these graphs, but you should know that the concept exists and these models exist. Now, assuming that the learning rate is the same for both models, the cumulative average time learning model represents a faster, it's this one here, represents a faster pace of learning. And how do managers choose which model and what percent learning curve to use? they do so on a case-by-case basis. Engineers, plant managers, and workers are all a good source of information of the amount and type of learning actually occurring on the production. Actually occurring as production increases. Okay. So that's interesting. This is cumulative average time per unit. Okay, so these are labor hours. You can see the labor hours going down, and this is cumulative total labor hours. This is the learning curve. So the learning curve goes up. Now, in this table, we see the predicted costs based on the cumulative average learning time curve. Okay, so here's our cumulative average. If we produce 1 unit, we expect that the average time per unit in labor hours to be 100 hours. Cumulative, so that if we go down to, like, I wish they had a nice 10, go down to 16, it's down to 40.96. Okay, cumulative total hours, 65.36 times $50. Okay, that's your cumulative cost at $50 per labor hour. The learning models we've been discussing provide managers with information necessary to predict costs. That's really why you use them. And they can also be used for performance evaluation. Wouldn't you just love to get evaluated that way? So the ideal database for estimating cost functions quantitatively has 2 characteristics. First, the database should contain numerous reliably measured observations of the cost driver and the related costs. And second, the database should consider the many values spanning a wide range of the cost driver. Unfortunately, management accountants typically do not have the advantage of working with a database having both characteristics. Okay, so let's take a look at some of the problems that are encountered and what we can do to overcome them. So managers should ask about these problems and assess how they've been resolved before you rely on the cost estimate. Okay, you've really got to take problems seriously and think about what the effect would be. The time period for measuring the dependent variable doesn't properly match the period for measuring the cost driver. This is really a major problem right here. You'd really have to know your business really well. Or if fixed costs are allocated as if they're variable. You know, whenever you see this, this is a major problem. Or finally, if data are either not available for all observations or they're not uniformly reliable. And you'd be surprised how much data is not available. Okay, if you ever search any databases for corporate information, like big databases like CompuStat, you know, some of the ones that we use at school, you'd be amazed at how many holes there are in the data where it's just not there. Other problems are extreme values of observations occur. Okay, if you've got a big outlier, so say you've got a graph that looks like this in a line and you've got a value that's way up over here, that's going to throw off all of your measurements. Okay, any kind of, like if you did a regression or a high-low method or anything like that. And finally, if there is no homogeneous relationship between the cost driver and the individual cost items in the dependent variable cost pool. Okay, a homogeneous relationship exists when each activity whose costs are included in the dependent variable has the same cost driver. Okay, so you understand, so you've got a variable cost pool, and some of the costs in there have different drivers. You know, that's a problem. So the solution then would be that the analyst would estimate costs separately for each activity or estimate the cost function with multiple independent variables using multiple regression. You know, multiple regression would resolve it. And finally, if the relationship between the cost driver and the cost is not stationary. So this can occur when the underlying process that generates the observations has not remained stable over time. Okay, so the solution would be to estimate the cost relationship separately for each period before and after the change. Then, if the estimated coefficients for the two periods are similar, the analyst can pool the data to estimate a single cost relationship. Okay, but that would at least take it apart for you. And finally, if inflation has affected the costs, the cost driver, or both. Now, inflation has not been a problem in your lives, but in the, let's see, in the early 90s I think in early 90s, was it the 90s? Yeah, and interest rates were like 17, mortgage interest rates were like 17%. Can you imagine? I stood in line at a bank to get a 14% mortgage. So that, things have really changed, but inflation makes a big difference because then your dollar's not stable. And the solution would be that the analyst should remove purely inflationary price effects from the data by dividing each cost by a price index on the date that the cost was incurred. Okay? The tricky part about doing that, though, is before you know it, it gets really complicated. Okay, we're done.